Hey, welcome back. Last time we were talking about the craziness that can happen when we're trying to take the limit of a function of multiple variables. And what we'd really like to be able to do is to talk about when a limit does exist and not just when a limit doesn't exist. So the way that we're going to do that is we're going to appeal to continuity. So we're going to talk about when we have a function that's continuous, then we'll be able to say what the limit is. So if you remember back from functions of one variable, a function was continuous if when you had that limit, the limit existed and it equaled that point. So same thing here. A function f of xy is continuous at a point ab if the limit as x, y approaches ab of our function is equal to f of ab. All right, so remember that means three things. That means the function exists at ab, right? In order for us to be able to plug in ab, we had to be able to put those in and the function has to exist there. So ab is in the domain. Second thing, this limit exists at ab. So no matter how we approach the function, from different points, then you got the limit existing. You got the same value. And the last thing is that those two values are equal. Right? Remember, you can have a function where the limit exists and the function has a value there. But if those two are not equal, this is not a continuous function. So when do we have continuity? Here are some good examples. So a polynomial, no matter whether it's a polynomial of just one variable or if it's a polynomial of multiple variables, like x squared y plus zw to the fourth. This is a polynomial. It's continuous everywhere. So no matter what x, y's, z's, and w's you use to plug in, you're going to get it's going to be continuous at any point. The other thing, so if you have a rational function like x squared minus y squared over x squared plus y squared, it's continuous on its domain. So if you look at this function, right, this function, its domain is everything except where x squared plus y squared is equal to 0. That's where we had that craziness happening in our picture that we talked about before. So what this means is if we take the limit as x, y goes to ab, or like 410 of this function, that is going to exist, and it's going to be equal to what happens when you plug in 4, 10. And then the composition of two functions is also continuous. The composition of two continuous functions is continuous. So for example, if we look at arctan of y over x, so we're going to say it's continuous on its domain, y. First thing, arctan, right? Arctan is the inverse tangent function, right? And so, right, the tangent function looks like this. The arctangent looks like this. And so arctan is defined on all real numbers, and it's a continuous function. So that's a continuous function. And then y over x is a rational function of x and y. And it's defined except where x is equal to 0. So defined where x is not equal to 0. And so if we took the arctangent of this rational function, it's going to be continuous everywhere that x is not equal to 0. So if we had something that said, find the limit as x comma y goes to 1 comma 1 of arctan of y over x, well, we would say this is continuous because it's continuous on its domain, just how we showed it. And so this is going to be equal to what happens when we just substitute in for y equals 1 and x equals 1. And then we need to remember that what value gives 1 when you take its tangent? The answer is pi over 4. All right, and so the consequence here is that if we know that the function is continuous at AB, which we have in some of those cases, then the limit exists and is equal to f of AB. All right, that was a quick video. We're going to stop there for now.